Hello, everyone. Welcome, welcome. We'll give it a minute or two here while people hop on, and then we will jump into today's webinar. Maybe 30 more seconds as I see people jumping in there, and then we'll kick it off. But I'll start with just a little introduction. So thank you all for joining today's webinar. Really excited to be diving into the benefits of laser technology for advanced manufacturing processes. If you're unfamiliar with Canada Makes, we are Canada's additive manufacturing network here across the country. We represent different laterals of advanced manufacturing in terms of additive and digital technology for additive. We are a network that really spans coast to coast with 75 members across the country, all again in that additive vein. Today, we're joined by Trump and Eliana, who will be leading our webinar today and walking us through what are the benefits of laser technology and how we can actually see them in real life via use cases and work that Trump has done there. I did just want to mention some housekeeping items. We do have a Q&A function at the bottom, as well, just the general chat function. So if you do have any questions throughout the session, feel free to pop them either in the Q&A or the chat, and we will have a Q&A at the end of the session today. And then as well, we are recording today's session. We'll be posting it on the Canada Makes YouTube, sharing it with you all as well. So feel free to share with your colleagues and your network if you find this impactful. As well, we'll be sharing Eliana's contact and information. So if you have any further questions afterwards that come to you, feel free to reach out as well. And without further delay, I will pass it off to Eliana.
Oh, thanks so much, Nicole. Thanks everyone for attending today. Really appreciate you spending the time to learn about TRUMPF Laser and what we have to offer. Very proud to be new members of Canada Makes. So obviously, I'm located in the US, and we also have America Makes. And Canada Makes is also a very similar organization, and just very, very interested to get in touch with you guys and find out what you guys are doing. And if there's any way that we can help you, we'd love to hear from you. But this is going to be a pretty interesting, broad ranging webinar for you, just talking about the benefits of laser technology as an advanced manufacturing process. I'm industry manager for aerospace at TRUMPF, and I've been at TRUMPF for about 5 years. I'm actually a material scientist by training. Got my master's and PhD at Imperial College in London, in the UK. But I spent most of my working career in the US. I spent 8 years working at the titanium company here in Henderson, Nevada, which is where I live now. But I also have worked at SpaceX and most recently in Los Angeles area for relativity space. So wide range of different manufacturing experiences and materials there. So hopefully you can see my screen, and I'm going to just break that down into an agenda of what to expect in today's webinar. I'll give you a short intro to TRUMPF, and then I'll talk about a refresher on lasers and where they're used in industry. Then we'll go into a section which focuses on aerospace, medical, and automotive. And then we'll really get stuck into the webinar with lots of different examples of how lasers can help you. And I'll finish up with a few success stories, which is always nice to hear, on real world examples, and then how you can follow up to learn more and get in touch with us. So TRUMPF is a 100-year-old family company. Please remember to pronounce the F. It's actually a German company. We're located in Ditzingen, Germany, which is just outside of Stuttgart. If you've traveled to Germany lately, you'll know where Stuttgart is. It's a technology leader in basically two areas, which the first is machine tool. So that is anything to do with flat sheet metal, bending, cutting, 2D laser cutting and welding, press brake type of machines that you're probably familiar with. And the other side of the organization which I belong to is laser technology. So that is anything that is used with a laser in 3 dimensions. So when I say 3D, I don't just mean 3D printing, I mean X, Y, and Z. And so basically cutting, welding, marking, surface structuring, cleaning with a laser, and then also 3D printing in terms of LMD, which is laser metal deposition, a form of DED, directed energy deposition. So that's what we get involved with. We have a presence all over the world with thousands of employees ready to help you in any country. And, a very sort of uh, storied history in innovation and development in technology. Think of TRUMPF as the Rolls Royce of the laser world, if you like. So let's do a quick follow on to lasers, what they are and where they're used in industry. So let's look at the basics of lasers. What's a refresher of a laser? What is a laser? So for example, a disc laser. So basically you have a lasing medium. So that could be a crystal, a disc, a fiber, etc. You create excitations and then photons are emitted. So photons are particles which have particles of light which have a certain wavelength, and then you use a series of lenses and collimators to focus the beam in the same direction so that you can either use that for concentrated energy, say cutting or welding, as I mentioned, brazing, drilling, ablation, marking, 3D printing, all those kind of things. So depending on what you do with the beam, how you let it spread out, how you let it diffuse, or how you concentrate it, it can be think of it as the energy from a typical hair dryer, but in the size of the point of a pin. So imagine all the energy that you use when you're drying your hair, about say 2 kilowatts or something like that, but focused down to the size of a pinhole. So that's a lot of concentrated energy that you can actually use for manufacturing. And so, like just an example here, whether you're doing things like surface hardening or you're doing welding, you're doing cutting where you blow metal, for example, liquid metal away. You can do drilling, you can do ablation, and you can do it sublimation as well. So there's all kinds of things you can do, which is pretty neat for the industry. It's a wide range of industries that we touch as well. So like I said, the main things that I like to talk about are cutting and welding. They're somewhat related. In cutting, you blow the material away. In welding, you let the material solidify. Then there's also surface structuring, which also includes cleaning and marking, so modification of the surfaces, putting marks, laser marks down on different materials so that you can read QR codes, logos, serial numbers, all those kinds of things. Or cleaning if you want to remove debris, organic materials, and that kind of thing. And the final part is the additive, which I've spent a lot of time on personally, and a bit more interest from you guys' point of view with Canada Makes. In this case, we used to have a division which did laser powder bed fusion. Unfortunately, we sold that part of the company. It's now a separate company called Atlix. So you may still see some of our machines around in the industry, but they are now run as a separate company. But we still do have the LMD, laser metal deposition, or DED, part of our portfolio. So you will go into later on in the webinar a little bit about some of those applications, and kind of exciting and interesting. So you can see a wide range of different things, from metallics to glass to polymers and ceramics as well. So broad range of industries, as I said. Machine tool is part of our organization, but I'm not going to really speak about them today because I actually from a different division, which is laser technology. We also touch in EUV, extreme ultraviolet wavelength, photonic components, electronics, and then also other sources, quantum technology, and something that we're really interested in, new space. So some famous applications of TRUMPF lasers. So you may have seen these around the world. If you've been to Los Angeles lately or you've seen it on the TV, you know they have a new stadium, the SoFi Stadium. But did you know that the panels at the SoFi Stadium have been cut and punched by TRUMPF equipment? So making thousands of these little holes for perforations, if you like, for airflow, and also they're decorative. That's one very useful, interesting application that TRUMPF got involved with. Another one which you might have heard of is our space laser. So this is a laser that was used in the Alps, and then fired a laser into the air, non-lethal laser, of course, and not blinding anyone, but basically used for lightning deflection. And also lasers are now on other planetary bodies. So there was a NASA rover named Perseverance, and one of our lasers was used to mark the nameplate on this rover. So we're literally in space. So right now we're going to focus in this part of the webinar on aerospace, medical, and automotive type of applications. Those are things I've been involved with lately. I'm not really an automotive guy, but I can talk a little bit about some of the things that we're kind of interested in. So examples of all kinds of high-tech and high-volume production environment products, from consumer electronics like an iPhone to automotive and e-mobility, so vehicles. So let's take the iPhone, for example, or a typical smartphone. There's lasers are involved in many aspects of this product. So from the chip manufacturing to cutting the PCBs, to doing marking, to modifying the glass, cutting, battery foil cutting, there's even additive manufacturing, drilling in the ceramics, texturing. Oh, I won't go over every single one of these, but you can see that there are lots of different things that lasers are involved with in making these devices. We also have a great interest in e-mobility and automotive, and interestingly, some of this also extends to the eVTOL aircraft that we're seeing more and more these days. So we think of things that happen in an EV automotive vehicle, for example, the battery cell module manufacturing, or the powertrain, the power electronics, or the battery packs. You can use lasers in all of these things, from things like cleaning and ablation of foils to welding hairpins, to doing things like marking, all kinds of things like this. So interestingly, even though I'm showing you right now an automotive application, for the eVTOL aircraft, like the air taxis and drones and things that we're seeing more and more these days, a lot of the same technology for the propulsion, the powertrain, are very similar. So it just happens that those things fly in the air, so they're considered aerospace. But really, the architecture is very similar to this. So lasers can be involved in all of these kinds of things as well. So it's really pretty staggering there. And then in medical industry, we have all things like endoscopes, we have marking, we have cutting, we have drilling, surface modification. So whether they're things like marking for machine readable codes, UDI, that's called, or welding, so very, very precision weld joints with excellent fit up for demanding medical devices. It could be cutting burr-free cut surfaces for things like stents, which go inside the arteries in a number of different materials, or surface modification, cleaning, making this kind of metal Velcro effect that people use on medical devices, which encourages tissue growth. So all those things can be accomplished with laser. My specialty area, which I'm more interested in, is aerospace. So that's traditional aircraft manufacture as well as space. I've spent a lot of time in my career working on both of those type of products. So for traditional aircraft, that's aviation. So it could be these aircraft structures, or it could be engine based. So it's airframe. It could be anything to do with cutting or welding long straights, or it could be drilling holes in some of the airfoils for airflow and so on. In space, it could be manufacturing things like engine components, fuselage components as well. And it could be also satellites, which is something that is very interesting these days. Almost every day, there seems like there's a satellite launch. For the aircraft, what kind of things can be addressed with laser technology? So, talking about the body, it could be removing paint and debris for coating when you want to give the aircraft a new paint structure. It could be things like drilling. It could be things like surface structuring. It could be building up worn structures using LMD, as we said. It could be welding. So there's a whole bunch of different things that lasers can get involved with. So, and then for space, there's all kinds of things. For example, launch rockets, something that is very interesting today. You hear about rocket launches almost every day. And indeed, Canada is also trying to launch their own rockets, I think, from Nova Scotia type of area. So you're going to see and hear about more of these things. These are really interesting. They could be joining, so straight up welding, things like fuel tanks and chambers and things. It could be creating new throttles, the nozzle, thruster nozzle structures using LMD. Sorry, I got a tongue twister there. And that's another thing where you can just build structures in a 3D sense without any supports. So that's kind of interesting. And then also making use of 3D printing for also ignition chambers and so on. So that would be using powder bed fusion or some kind of method like that. And then on the satellite side, yeah, there's also data relays, which are interesting. And just showing you some more examples of use in satellites. So whether it's cleaning or surface structuring for heat exchangers, so increasing the surface area on heat exchangers, or doing things like welding brackets, creating those by 3D printing. It could be joining dissimilar materials, so metal to glass, for example, or sapphire. It could be joining straight up welding, as we said, and waveguides and those kinds of things. So there's all these different structures that lasers can get involved with. Another interesting one, which we're just starting to work on, so we don't have too much data on this, but it could be using lasers for telecommunications. So smart networks using a combination of laser and radio. So as the need for more information and faster services, data services is required. That's why we're launching so many satellites in the air. You've also got to get a way to get the method of transmitting the data. And this could be something where lasers can get involved with. So like I said, I don't have a huge load of information on this, but you'll hear the terms more and more as we move into this age where everybody needs information on the device that's in your pocket. So right now we're going to go into some interesting examples, and I'm going to go into sections which are grouped by cutting, welding, joining, surface structuring, marking, and so on, and then also LMD. So I'll break those, even though they're individual sort of examples, I'll break them into basic clustered sections so you get an idea of where we're going to go. So I'm going to start with cutting. So cutting you can do on very simple 2D sheet metal. But what if you had an example of a product that had 3 dimensions? So this is where we're going to talk about the need for creating high quality laser cuts with low amount of roughness, no burr or burr-free surfaces, small heat affected zone, HAZ, and small as possible recast layers. So this is some work that was done at TRUMPF in Germany. So this is comparing different typical materials, stainless steel, titanium, aluminium, and then just looking at how the precision of the cutting, so basically measuring surface roughness, can be done. And so in a series of tests, we determined that the roughness can be reduced by 30 to 60% depending on the parameters that you use, and featuring a true laser cell. So a true laser cell is basically a laser contained within a safe box. So whenever you do laser processing, if you need to protect your eyes, you can build your own cell. If you don't have your own dedicated cell, you can buy a cell, which is like basically a machine with laser safe doors that you can access, and the laser only turns on once the door is closed so that no one's eyes are going to be damaged. So we found that using this kind of setup, we can achieve these kinds of reduction in roughness. And then some interesting parallel type of tests that we did in our lab in Michigan in the US, also using a different kind of machine, True Laser Cell 3000, True Laser Cell 5030, which are the small to medium sized machines. These machines are also really used a lot in automotive cutting as well, but we extended that sort of know-how to cut typical aerospace grade materials. So 316 stainless steel, Ti 64, 6061 aluminium, and 718 nickel alloy. So what we did here, we used a 4 kilowatt fiber laser for maximum power. We used this ISO standard here, which I've put in the notes here, as a guideline, and then try to look for the minimum presence of rejectable defects according to that guideline. And what we found was not every material that we did the cuts on were 100% perfect, but on the whole, with the new parameters and trending towards looking for these kind of defects on large smooth arcs, you can cut with excellent surface, with excellent fast speed, no cracks, and a minimal recast layer. So according to using this spec as a guideline, we got great results with a variety of different materials. So what that means basically to the manufacturer is if you're looking for this as a process, you're going to now be able to have good quality cuts overall with minimum material waste and reduced need for rework. All those things lend to driving costs down, being more productive, and then also having a knock-on effect on your amount of inventory and things that like rejectable products and so on for defects. So these are all good news. Related to cutting is welding. Like I said, when you are using a laser on cutting or welding metal, for example, or metallics, what you do is you will get the interface molten, and if you're cutting, you blow that molten material away. And if you're welding, all you do is just let that molten material solidify. So you can basically think of welding and cutting as two sides of the same coin. So for joining or straight up welding, structural components, whether they're things like fuel tanks or those kind of pressure vessels, tubes and vanes and things like that, you can make straight up welds. And then here's a couple of detail of how you can make your welding process more efficient. You benefit is reduced input energy into the workpiece so that you only put the minimum amount to achieve the strength of the joint that you need. So you can move relatively fast. So again, you're improving your throughput. So whatever meters per minute that you use. And you can have a large area addressable by using a scanner for your welding as well. Another benefit, if you use shielding gas, is to keep the oxidation of the molten area down. So this is very helpful for things like titanium, which is very susceptible to oxidation in the molten state, and other materials like aluminium, Inconels, so nickel alloys, and stainless steels. Another thing you can do with laser joining is joining dissimilar materials. So this is an example of a carbon fiber reinforced polymer with metallics for structural components. So how do you do this without needing an adhesive or rivet or mechanical fastening? Only thermal activation. So a kind of two-step process. First, you would structure the metallic to be joined by roughening the structure so that it's more easy to accept the polymer inside. And then you melt the polymer so that it's not completely molten, but merely plasticized so that it's enough to heat is enough to make it flow. And then the liquefied plastic or resin infills in the cavities so that after it's solidified, a strong bond is created. And so this is ideal for thermoplastics or, as we said, carbon fiber reinforced polymers. So you're really creating a dissimilar metal joint, which is strong enough for the application. Another one to do adhesive-free joints would be using ultra-short pulse lasers. So again, you're not introducing a chemical into the process of joining, so no gluing is required, and you can create a gas-dense joint. So you don't have to worry about the mismatch in thermal expansion coefficient. Virtually any material combination can be used. And this is especially great for things like glass. So trying to join these kind of dissimilar materials together. So an example of this would be joining silica glass to metal like copper Invar, or joining sapphire glass to Invar as well, which is what we've shown in this image here. And this process has even been qualified by NASA, so that's pretty cool. So as another sort of extension of that, we have this high-speed LMD process, so laser metal deposition. And you can think of a LMD structure as a big giant weld. So we're basically applying molten material on top of itself. And in this case, this is also another learning that has come from the automotive world, where you're trying to create a dense corrosion resistant coat with very high material efficiency. So you can move pretty fast. You can deposit the layers as you required. For example, this is on a rotating spindle, and you have metallurgically bonded layers. So you have a very good final strength. This is what we call the ELA principle. So there's extreme high-speed laser application or laser cladding, you'll see it's called, which is used a lot for repair in brake pads and things like that in the automotive world, but also can be used for anything that has a friction or wear resistant requirement added. So this one, for example, is adding 625, which is a nickel alloy, using this high-speed layer on to a substrate of a stainless steel, and very good coating resultant. So very low dilution and small heat affected zone. So that's all good news. And then extending that also to not just building up new structures, but also repair. So repairs, we said, something that is very interesting in aerospace, where you want to not throw away a part and start all together with a brand new part, but you can extend the life of an existing part. So when you're thinking about repairing something that's very expensive or something that's sensitive, you've got a solution for that here. Nearly any metallic alloy can be used. You just have to adjust the build rate and the heat input. So here's an example of creating blades. This is for aerospace, using a local shielding gas and then repair. So I think this was demonstrated actually years ago on a Rolls-Royce seal segment. And but it can extend to any kind of structure that you think you can imagine. This is just adding more material to some place where it's susceptible to wear or friction or even damage from birds and things like stones and pebbles or debris in the air. So if blades are deformed, the workpiece can be scanned and then repaired using adapted tool paths with software. So we're injecting a bit of the intelligence into sort of automating this kind of repair process by LMD. And then LMD also can make these huge structures. Sorry, I had a tongue twister before. I got my tongue all over the place. But imagine you are making a nozzle extension for a rocket engine. So, for example, second stage rocket engine, vacuum rocket engine. So, um, just laying down, think of it as laying down one giant weld and then moving in a section where you need to have a very good structural component. It could be as high as 6 feet, so a meter and a half in length in the Z height, for example. And how do you do that? Well, it's more difficult to do that with laser powder bed fusion, but you can do it with LMD because of some of those restrictions. You're not constrained by the build envelope of a powder bed chamber, but you just use blown powder to put the material where you want it. So this actually has the lowest material costs and the highest part properties of any AM process. And a good example of this, which was developed by TRUMPF, was using a green laser wavelength for the highly reflective materials like copper alloys. So we've done this on GR 42, which is it's a NASA developed alloy in copper, and also copper chrome zirc, which is also very commonly used. And with these, the build-up rates can be much higher because you're not getting a lot of lost energy in laser energy from the reflectance of the material. So more of the laser light is being absorbed into the material, which makes the process more effective. And no support material is needed. So it's a much lower powder consumption than powder bed fusion. And you can also use this on other materials like nickel alloy 625, 718, and so on. If you were to control your oxidation, you could also use it on titanium. And here's an example. So I did have this example of this nice image on the front page of my webinar, but just showing you some build-ups here with the green laser. So this was using up to a 3 kilowatt green laser to make these kind of nice structures. And so some of our customers have actually used this on real components, not just rocket engine, but also thrusters and small thrusters and so on, and successfully conducted hot fire tests, which are kind of interesting. So typically the factor is about 10 times less powder consumption compared to a powder bed process. Can also use the same kind of process to make these large pylon structures. So as I was saying before, in aircraft, you could be interested in things like seat tracks that are really long and they go on for the entire length of the aircraft, for example. So you could imagine this kind of AM process limited to LMD, a solution for any size. So people are thinking big these days. You may have seen a 3D printed bridge in Amsterdam. So the bridge has to go over the canal. And that was also an interesting example of where DED could be used to solve these problems of making these large, unique structures. So building up these structural components, yeah, you can use a local shielding gas to avoid oxidation. And then, manufacturing these parts, you can scan in the design using the software to calculate where to tell the laser to go. And then, different range of materials, but also very much used 718, again, Ti 64, very commonly used materials. So we talked about cutting, we've talked about welding, we've talked about LMD. Now we'll go on to more of the surface level type of application. So this is going to be marking, structuring, and so on. So why do we do laser marking? Well, it's always good to be able to laser mark your name onto your pen. So I always know where my pen is, and my pen belongs to me because it has my name on it. But also if you need complex parts, you want to have those serial numbers parked for traceability, reusability on. So you can use a laser to mark on basically any material. We've even marked things like wood, but typically those will be polymers, metallics, glass, things like that. You can mark your own name tag. So whatever it is, QR codes, UDIs, barcodes, and so on. You can even use that to mark on these wires. So very, very tiny, precise marks. You can use the laser in the opposite way to remove some of the top surface so that you also get a kind of engraved type of effect as well. And those are important for things like vision systems or interfaces where you need to rapidly scan something. So you can also think of that in the cleaning method. So going back to aerospace, cleaning turbine blades. So for example, if you want to selectively remove dirt, debris, oil, and things like that, and maybe you want to follow that with a LMD process. So you do the cleaning, then you do the deposition. So you can do that as well. So you can remove material without having to affect the material underneath. You just remove the very top surface layer using, you can do that using an ultra fast laser, for example, a nanosecond. And so that has different absorption properties between the top and the bottom layers. So you only selectively remove the thing that you want. This is another great solution because it avoids having harsh chemicals in your shop or your lab. Another one you can think of is to create functionalized surfaces using a layer. So again, we're only concentrating on the surface. So basically surface roughening, things like that, or creating different, what they call functions. So you remove paint layer, predetermined areas to improve electrical contact, or you do a surface roughening to improve adhesive if you're going to use adhesives later on. Or you can create a greater surface area by making metal Velcro that also increases surface area for heat exchangers. So anything you want to do like that, that is also possible, and a wide range of materials and feature sizes that you can use. You just change the beam and raster that in a different way. We can also look at precision cutting with the ultra short pass laser on things like glass. So glass, you think is a pretty difficult thing to cut, but you can use a laser on it and it has a kind of no contact, no tool contact, an easy process to set up. And then you basically just tell the laser where to go and you can directly cut the thickness up to 10 millimeters feasible. And because you're using a laser and not a tool, you have a very low risk of cracking and damage because it is a touchless process. So you're not inducing stress into that process. So it's very handy for things like that. And then also, if you wanted to do some more surface work here. These are on bipolar plates. So again, fuel cells, so zero defects and low amount of stress induced into the process because you are using a laser, wide range of materials and highly automatable. Automatable, is that a word? I think so. It's the process lends itself to automation, let's say. So let's look at some success stories of where we want to go with lasers. And so, as you can imagine, a lot of our work that we do for customers is covered by NDA. So I'm sorry I can't show you a whole bunch of really cool things, but I can show you some cool things. And so there are examples of customer success stories where they've used our lasers in their advanced manufacturing process. So whatever they are, whatever the process is, cutting, welding, marking, and so on, and what their sort of testimonials are, if you like, you can think about this as a learning process of how it relates to your product. So let's say it's cutting for medical, and then you have a very nice burr-free cutting. You want to do precise, small dimension, really, really small cuts, including sublimation cuts and things like that, stent cutting, to vaporize material or to minimize the amount of post-processing that you do. This is something that you can do it's used very widely in medical industry. So And like I said, on the structuring, oh, just wanted to show you a couple more images on the surface structuring. You could also use that for colorization. So particularly on titanium, you can adjust the thickness of the oxide layer, which refracts light at a different wavelength to give you different colors. So instead of using traditional anodizing process, which involves liquid, you can use a laser annealing as an alternative to chemical anodizing, and that can also get you very similar colors to what you can. Purples and blues and golds and things like that turn out really, really well. So those are all something that you can do. Now, let's talk about the success stories. So I was on about cutting. So this is a customer called Alpine Laser, and they're using our lasers to create tools or machines that they use for stent cutting in medical. So things like catheters, stents, and so on. Very, very fine material. It could be stainless steel. It could also equally be nitinol, which is a alloy of titanium and nickel. So, for example, in this tiny tubes, 0.25 millimeters in diameter and a wall thickness. So this benefits if using the laser, really excellent surface finish and minimal post-processing. The speed is an advantage, so 2 to 5 times faster than conventional machining. And then they use our laser and then they package that into their own machine and they put their own label on it. But these are kind of things that you'll see. They do a lot of work in North America, and you can see that's a kind of ultra short pass. In this case, it's a femtosecond laser that they use, and then they have a process to basically hold the material and do that. Oh, it moved by itself. This one is a customer called Carl Stores. So basically, this is welding eyepieces for medical endoscopes. And Carl Stores is a German customer, but they're also used in many other applications, including robotic surgery these days. So these just happen to be stainless steel, and then the weld seam has to be completely leak tight with less than 1 millimeter thick. Attach that to a robot that also removes the welded parts and then inserts two parts so you can have it semi-automated. And using the robotic welding reduces the time from 10 seconds to 1.5 seconds. So 1.5 seconds to make a weld. So really you can improve that process a lot and speed up your production. And then finally, there's this customer here, which is called Sign Fracture Care. So this is creating marks using a laser which has to survive the process of cleaning and going into ultrasonic cleaning, passivation, and steam autoclave. So instead of using typical marking, you do a permanent mark with a laser that can never be removed. And so the benefits is the TRUMPF products also integrate into their manufacturing process. So again, an advanced manufacturing process, ERP system with a vision system to scan the job traveler codes, identify the parts, and then pick up the tools and match those to the relevant part and then make the mark. So we worked very closely with them to pick the right parts, get the right product, and then figure out the process of how to do that while meeting FDA and ISO requirements. So very good real world examples of how to do that. And so I think we are at I can't believe we're at the like 45-minute mark. But the TRUMPF team is here to help you. So if you are interested in working with us or finding out more, you can just use our website for informational purposes. We also put out many informational videos on YouTube. So we have a YouTube channel, which is called TRUMPF2. Please don't forget the F. But you can go there and you can look at a wide variety of different tutorials and know-how videos. You can download a white paper, or you can book a time to talk to us, or you can come and see us at many of the in-person events. So we will be in Canada in April, we will be attending the Aero Montreal conference. Hopefully, we'll be attending more Canada Makes meetings in the future. And we may be attending MMTS with any luck in the late spring. So with that, I would love to hear from you. And if there are questions, I think Nicole can help us take the questions in the chat if you have anything in the chat. But
Certainly.
thank you so much, guys. I really appreciate you.
Awesome. Thank you, Eliana. That was awesome. I was gonna say your Trump inscripted pen. I also have one from Trump that has my name on it that I still use to this day. Thank you so much for sharing all of that information. It was great to really understand all of the use cases for laser technology. I
It's a
will.
lot. I know it's like a lot. There's so
uh,
if it doesn't go in all at once, don't worry about it. That's how we're here to have a conversation.
Excellent. Well, I was going to suggest if you have any questions, feel free to pop them in the chat. I think we can also raise your hand if you want to go off mic. Um, and maybe we'll give it a minute or two here and see if any questions come in. But in the meantime, I'll just reiterate we did record this session, so we'll be passing along the recording. And I wanted to confirm, Eliana, if you were okay with passing along the slides to share as well.
Yeah, I'll make those in a PDF.
Excellent. So we'll pass that information along to all of you. And then as well, we can have continue that discussion afterwards if there's any questions. We do have one. So Bob from I'm Manufacturing. Hello, Bob, a fellow also Canada Makes member. Does Trump have any wire slash laser LMD systems?
Interesting. One of our partners does a wire feed head. So we do have a laser system, LMD system out in the wild with wire, and they were set up with so one of our partners, Press Tech. So if you need to get put in touch with them, I can put you in touch with them. But we don't make we only really make the nozzle for LMD for powder. They can help you with a wire setup, but they use our laser, obviously.
Excellent. Another question here. How does dissimilar material joining work? Example, glass to something else. What is the mechanism for adhesion?
Yeah, so there's different methods for that. So instead of you're not really creating a metallurgical bond because you can't. So all you are doing is increasing the surface layer. So some of those for dissimilar are making like a mechanical key where you can make gaps in the metal and then you can make the whatever other material flow into it. So, for example, that one with the polymer. So it makes like a mechanical key. So you're not really creating a metallurgical bond because you can't. Sorry, I'm drinking water here. It's not beer. It's too early for that.
You're a couple hours ahead of us anyways on the West Coast, you know?
Oh no, it's not even 10 o'clock here.
Oh,
It's
right, it's
yeah,
behind.
yeah,
You're
yeah.
behind.
You're
Right,
ahead of
right.
me. You're ahead of me.
I'm a couple hours ahead of you.
Guys might be allowed.
Yeah. Awesome. Well, I don't see any more questions coming through, but again, we'll reshare all of the contact. Oh, never mind. Bob again here. Thanks for the question there, Bob. Um, the 2M slash min, which I'm assuming is millimeter slash something, feed rate is really impressive for DED. What system accomplished that? Meters and slash minutes.
Oh, so for DED, typically what we either sell the laser and the optics and the chiller itself, and then a nozzle, powder nozzle, or we do have DED available in one of our cells. So we have two cells, which are like a ready-made laser in a box, a safe box, if you don't have your own welding cell that is laser safe already. So some people buy those. Uh, so it's a True Laser Cell 3000. That's a smaller one. That's about the size of a closet. So if you want to use that for a lot of the things that maybe you've seen, I think I have. Yes, this little grid fin here on the left-hand side was made in one of those True Laser Cell 3000s. So this one's not very big. It's about 6 to 8 inches. But that's the kind of thing you do if you want to do prototypes. If you want to make some of those larger components, we have a big cell, which is called the 7040. That's like 4 meters long, and you can do LMD or DED in one of those. Interestingly, one of our customers in the UK wanted like a bigger Z height, and it's only really, not including the table, a meter high, so it wasn't enough for him or them. Sorry, I should say. So what they did is, very interestingly, they dug a pit. They dug a pit in the floor. So that's how they extended their Z height. So they made it in a really, really huge, I know it's a structural investment to their building, but that was possible. So that's how they accomplished that. Um, but yeah, so you can either do it with a combination of just the laser and your own cell and your own setup. And so some people will put it on a robot. So we also have a customer in Colorado who has a robot, and then they built their own cell. So we sold them just the laser, the chiller, and then they got the wire feed head from someone else from Prestec, and then they got their own robot. So there's different ways to do it, and there's different sort of setups depending on what you need and what. It really depends on the size of the part that you're going to make and whether you think you're going to continually use your custom cell, which is usually something you have to build yourself. We don't do the building, but we also have a couple of integrators that we work with where we can recommend that. Or if you have someone local who has helped you, they probably can help you. If not, then you buy the ready-made machine and it's already in a box. So those are the two options.
Excellent. One more as well. What's the difference between green and blue laser for copper?
Yeah, TRUMPF does not make a blue wavelength laser. So the green is at 515. I think the blue is like a 435 nanometers, if I remember right. And most of the other lasers that we use are infrared. So they're all 1063 or 1060 or 1070 nanometers. So the infrared laser will be beyond the visible range of light, but a green laser is in the visible spectrum. So you see it being green. I think I had that in the, sorry, I've got to go, I've got to go all the way back. Oh, here it is. Yes. So, I mean, I think it's an illustration, but when it is working, it actually does come out at green. So the advantage of this is that with the infrared wavelength, you'll get a lot of wasted laser light because the material itself is reflecting a lot of those wavelengths away. So when we use a green laser, something like copper, aluminium, even gold and silver, they're reflective materials. So they will reflect a lot of the laser light. With the green laser, they will receive more of it. So less of it is being reflected away. So that means that there's also less damage to your equipment. There's less spatter and there's less particles being thrown into the air. So you get better productivity. You can get a faster speed that way. And so that's the benefit of working with a green laser. And that actually came from the cutting and welding world of welding flat copper sheet for things like electronics or anything that's highly conductive. So that's where it came from. And then it extended into 3D printing with the LMD. So yeah, that's the idea of using the wavelength. But blue, I'm sorry, we don't make. But other people have used blue, and I have read a couple of papers on it. For us, it's always been green because we developed that from the cutting and welding world.
Awesome. Perfect. Well, with that, as mentioned, we'll send out an email this afternoon to you all. I wanted to thank you, Eliana, for joining our session today and really hosting it. It's been a great overview, and I think lots to take away.
Thank you so much. And I really appreciate your questions, guys. We are here to help. There's lots of informational things you can find even if you're just learning for educational purposes. We have a lot of brains trust type people who are pretty smarter than me, but they spend their whole lives working on laser technology and laser processing. So really, if there's anything that you can't find easily, just let me know. I can probably try and find it for you. Like I said, there's a lot of information out there. Some of it is unfortunately NDA protected, but if there's things like you've heard a TRUMPF presenter at a conference, or you met someone and you really enjoyed their paper, we can try and get a copy for you. So just let us know, and we're here to help. Like I said, we are proud to be members of Canada Makes, and this is our first year of membership. So we're eager to find out what people need and what they're looking for and how we can get involved. So definitely see Canada and you guys as huge contributors to North American manufacturing is very important. So, especially in this day and age, I need all the help we can get. So, if we can be part of the partnership and the ecosystem, we'll love to hear from you.
Awesome. Thank you so much. With that, we can close today's session.
Thanks,
Awesome.
Nicole. Thanks so much.
Thank you. See you.